Hello everyone, I will talk about the memory model with a general interface for representing memory structures called the nominal memory model and its application to the verified compilation of C programs. Memory models play important roles in verified compilation. This figure shows the structure of a typical verified compiler. The source program P1 is compiled into the target program Pn through a sequence of transformations. To prove this compilation correct, we need to show the semantics are preserved by every compiler pass. For this, we need to define the semantics of every language based on certain memory models, and we need to establish certain memory invariants for each compiler pass. The most widely used memory model is the block-based memory model for CompCert verified compiler. In this model, a memory state is represented as a collection of disjoint memory blocks, each with its unique identifiers and a linear address space. A pointer is a pair of block IDs and offset into the address. The pointer arithmetics are performed by adjusting the offset while keeping the block IDs unchanged. This, by definition, provides the isolation between different memory blocks. Memory invariants are defined by injection functions, which are partial mappings from blocks to blocks plus offsets. The bottom right figure displays an example describing a certain memory transformation. The injection function J maps the source block B1 into the beginning of the target block B', and the B2 into the middle of the target block B'. The source block B3 is dropped because it is not in the domain of the injection function. Despite the previous success of the block-based memory model, it still has a lot of limitations. For example, block identifiers must be positive numbers. A special identifier called nextBlock designates the next available block to be allocated. It must be incremented by 1 upon each allocation. The blocks already being allocated are called valid blocks. They are numbered consecutively from 1 to next block minus 1. This creates a lot of problems in verified compilation. The bottom right figure displays a memory injection for a compiler pass for eliminating unused global variables in CompCert. In this example, the second global variable is dropped from the memory. Because the target memory blocks must be numbered consecutively, all the source memory blocks allocated after block 2 must be shifted by -1, including the stack blocks which are not supposed to be touched by this transformation. This example illustrates that the concrete and the consecutive numbering of memory blocks creates unnecessary dependencies between different kinds of memory blocks. In turn, it creates unexpected complications in memory injection and in the proofs of compiler's correctness. We ask the following questions. Can we remove the previously mentioned restrictions of the block-based memory model? If so, how and what benefits can be derived? A lot of previous work on extending CompCert has tried to solve these problems, but their solutions are all quite ad hoc. In this work, we propose a systematic solution to those problems. Our solution is to abstract over the block-based memory model by using nominal techniques, which is a collection of mathematical devices for managing named resources. In particular, block identifiers are generalized to any type with decidable equality, which represents nominal names. Valid blocks are generalized to an abstract data type called support, which provides a more general notion of allocated blocks. When allocating a fresh block, instead of inspecting next block, we call the method fresh block provided by the interface of support. With this more general memory model, the block-based memory model simply becomes one of its instances. With the nominal memory model, we have eliminated the unnecessary dependency between memory blocks mentioned before. Based on this, we have developed the nominal CompCert, a complete extension to CompCert whose proofs are parameterized over any instance of block identifiers. By instantiating nominal memory model with rich memory structures, we get much more intuitive proofs for the key memory transformations in CompCert, including the elimination of unused global variables as described before. We also developed the multi-stack CompCert. It is the first verified compiler that supports contextual compilation to a multi-stack machine model. Note that because of the systematic generalization provided by nominal memory model, all the existing mechanisms for block-based memory model, including memory injections, still works.